Hi, welcome to another episode of Humanism Today, the podcast where we dive into ideas, stories, and conversations that inspire humanist freethinkers and like-minded people. This podcast is presented by the Humanists and Freethinkers of Fairfield County in Connecticut. Our motto is compassion and reason. Compassion means that we care about all people and their rights regardless of their status in society or their personal condition. Reason means that we use science, facts, logic, and scientific methods to find the truth.
I'd like to introduce tonight's program, which is on space, and to welcome Dr. Lachlan Lancaster, whom I know personally since he was in middle school. So I'm very proud of him. And to introduce him will be a colleague and longtime friend, my son, Brian James, also a doctor.
It's my pleasure to welcome Dr. Lachlan Lancaster. He is currently a Flatiron Research Fellow in the Center for Computational Astrophysics at the Flatiron Institute, which is sort of the internal research arm of the Simons Foundation, where he's been investigating the complex gas dynamics and observable properties of star-forming regions, which I'm sure he'll explain all that jargon to us today and more. Lachlan has previously been at Columbia University as a junior fellow in the Simons Society of Fellows, and before that completed his PhD in astrophysics from Princeton in 2022. So without further ado, I'll turn it over to Lachlan to hear more about our place, Earth, in the universe.
Thanks so much for coming out today, everybody. I think the first time I came here, Anita asked me to talk to you guys about dark matter and dark energy, which are I think they draw a lot of public interest because they sound so mysterious. And I'll probably talk about them or touch on them a little bit in this presentation as well. And then last time I spoke about my own research, which was on star formation, and contrary to what Brian might have hoped, I probably won't talk very much about star formation at all. Unfortunately, I'll very, very briefly talk about it. Anita asked me to talk about recent stuff in regards to popular science fiction and the Artemis program. And I thought I would give a little bit of a different perspective on that by trying to give you guys an idea of our place in the universe, like where we are, where we come from, and how special it is. In particular, I hope that you are convinced by the end of this that the idea, and I'm not saying that this is necessarily promoted in the recent science fiction or literature, but I think it is kind of out there, this idea that we can leave Earth, and if there's problems on Earth, we'll just go somewhere else and it'll be okay. And I would like to disillusion you of that perception if you thought that was the case. So does anybody know this picture? Has anybody seen this before? Pale blue dot. Yes. Nobody. Okay. So if you don't know, that's Earth. This is a picture from the Voyager 1 spacecraft taken in 1990. And Carl Sagan, who was a professor at Cornell University, well-known astrophysicist, maybe many of you have heard of him before. He was a big proponent behind the Voyager 1 spacecraft, and he advocated for the camera of the spacecraft to turn around and take a look at Earth when it was very, very, very far away. I'll give you a better idea of just how far away it was when it took this picture. So just to give you an idea of that everything, like all of history, everything that we think of on the Earth and everything that we have ever imagined, all wars that were ever fought were fought over this, which is actually less than 1 pixel in this camera. So a little bit of this is our perspective. So here's the outline that I want to give. Some questions that I would like to give you some perspective, maybe not answer entirely, but first, where are we? How do we get here? David Byrne, if anybody knows that reference. Okay, so where are we? I already showed you. You are here. Let's go through I want to give you a sense of scale. Hopefully you enjoy this kind of sense of scale thing. So this is the sun. We're going to start at the center of our solar system. nearest star to us, obviously. Each slide that I go through here, I'm going to zoom out by a factor of 2. Okay? So we're starting to zoom out, and everything should be to scale. Things will disappear and come back, but everything should be to scale as we go out. So the sun gets smaller and smaller and smaller until eventually you get to the orbit of Mercury, which is relatively close to the sun. We zoom out a little bit further, we get to the orbit of Venus, one factor of 2 larger. There's Earth. Okay, so here's the inner solar system pretty much entirely. You can see the orbit of Mars peeking in at the edge of the slides. This is the very, very center of the solar system where all rocky planets that we know of in our solar system exist. Zoom out another factor of 2, we have Mars. Another factor of 2, we see the orbit of Jupiter. The classical asteroid belt is between the orbits of Mars and Jupiter. That's where all of the things that, or 99% basically of all asteroids that hit Earth come from the asteroid belt. So that's just between the orbits of Mars and Jupiter. Another factor of 2, we get Saturn. Then another factor of 2, we get Uranus and Neptune. Another factor of 2, we get Pluto. And finally, we see where Voyager 1 was when it took that photo of Earth. So just beyond the orbit of Pluto, the mean orbit of Pluto. I should say also that I made these all circles. The actual orbits of the planets are elliptical and they don't look quite like this, but that's just for scale here, or for simplicity. I didn't want to make perfect ellipses and center them all correctly. Another factor of 2, we still are kind of seeing where Voyager was, and then another factor of 2, we're out to where Voyager 1 is today, which is about 1 light day. So it takes about 1 day of time just to send a signal to Voyager and to get something back. And it's still going out further and further. Okay, another factor of 2, another factor of 2. We see kind of very barely where Voyager is. Another factor of 2. I've taken everything out except the orbit of Pluto, which is going to get smaller and smaller until it's very tiny. Now I've zoomed out the scale. This is 1 light month. We keep going. That gets smaller and smaller and smaller. We get to the edges of the Oort cloud. The Oort cloud is basically a bunch of rocks that are sitting around our solar system that are there from when the solar system first formed, and they're basically on extremely long period orbits. Then they just sit out there doing nothing. It's a bunch of rocks very far away. And they occupy a relatively large amount of space, you would think, at least on this scale. We keep going, 1 light month, another light month. We reach the edges of the Oort cloud, which the very, very edges, this is a little bit of an overestimate probably, but the very, very edges are almost a light year away from the sun. We keep going, another factor of 2, and we get to the nearest star to us that is not the sun, Proxima Centauri, which is about 3 light years away. And it is at this point that I realized I was spending way too much time making this very nice circular video, and I was like, okay, I need to go to NASA and get some pictures of this instead. So I went and found a nice diagram that somebody had already made of the nearest star systems. And now again, this is another factor of 2 still, so still to scale. And we zoom in again, we see Proxima Centauri, and then the 10 nearest stars laid out around us. Okay, so that's all been factors of 2. And now we're going to zoom out a lot and go to the size, the scale of our entire galaxy. So this is a editorial depiction of the Milky Way, the entire Milky Way galaxy that we live in. We live about 26,000 light years from the center of the Milky Way. So it takes light 26,000 years to get to the center and back. 26,000 years, yep. So general relativity tells us that when motions become comparable to the speed of light, you need to reconsider how gravity works, okay? And so you might think that on these scales, and since I'm talking about things in terms of light years, that we might need to take general relativity into account when we talk about the dynamics of galaxies. But that's not actually true, because the dynamical times of galaxies are much, much shorter than much longer than the light crossing time of the galaxy. So it's totally described by Newtonian dynamics. To give you an idea of that, so the light crossing time is maybe a few times this, so on the order of 100,000 years. It takes about 200 million years for the sun to orbit the galaxy. Okay, So this is the Milky Way. Again, we are a solar system in the middle of a disk galaxy. So we're looking face on, top down at the top of a galaxy of stars. Our sun is right in the middle of that disk, and that's where the Milky Way gets its name, because if you look up at the night sky, and if you either have really, really good eyes or a really, really good camera, and you're in really, really dark skies, then you can see on the night sky that there are more stars in a plane than there are off the plane. And we're sitting inside a disk of galaxies, right? And that is a telescope that has a laser. The laser is used for a thing called adaptive optics, but that is pointing basically at the center of our galaxy. That's the constellation of Sagittarius. All of that dark stuff, so you see that there's light and stars all the way through there. There's also dark stuff that's blocking out some of the light. That dark stuff is gas and dust, which is what the stars that are living in the galaxy form out of. They basically collapse under gravity until they cool and condense until eventually you get something so dense that it ignites nuclear fusion. That's a star. Okay, back to our scale picture. We are, again, 26,000 light years away. Zooming out again, so that was remember we went from maybe 10 light years to 26,000 light years. That's maybe a factor of 1,000. Before I was going factors of 2. So that's a huge jump. This is our galaxy. This is the local group of galaxies. So this is sort of all of the galaxies nearby us in the universe. And when I say nearby, I mean within 50 million light years. Okay. 50 million light years. So now it takes light 50 million years to get to these galaxies. And here you can start to see, so every point in this picture is a galaxy. Not all of them as massive as the Milky Way, but they're all galaxies of billions or tens of billions of stars. You can see that there's structure. This is the Virgo cluster, which is the most massive nearby cluster of galaxies. There's the Fornax cluster down here. So there's some sort of structure in the universe, but there is lots of structure, in fact. But if we started to zoom out, so again, 26,000 light years to 65 million light years, that's another factor of 1,000 or so. Really, yeah, a few thousand. We zoom out even more, so now I'm going from 65 million light years to about 1 billion light years, so a little under a factor of 1,000. But basically, so before, again, factors of 2 out to the solar system, and then factors of 1,000 out to the large-scale universe. This is a picture from a simulation, so this is, again, the other things were basically diagrams or artists' conceptions, other than the picture of the night sky. That's real. And this is a simulation of structure formation in the universe, showing the large-scale structure. So you can see, if you zoomed into a little patch here, there is lots of structure, but as you zoom out further and further and further, the universe is basically what we call homogeneous and isotropic. There is no preferred direction or preferred place. Everything looks, for the most part, the same on large scales. And you keep going, another factor, well, a factor of a few, or a few tens, 40 billion light years. Eventually you reach the cosmic microwave background. We call this basically the afterglow of the Big Bang. And this is the edge of what we can see in the universe. Because the speed of light is finite and the age of the universe is finite, if you keep going back and back and back and back as far as you can go, eventually you reach basically the beginning, and that's this. It's very close to the beginning, not quite the beginning. So this is the edge of the observable universe, at least things that we can observe through light. There's no light that goes beyond this. Okay, so now we have some idea of where we are, at least from the smallest scales up to the largest scales. David Byrne, again, coming here to ask, how do we get here? This is sort of a timeline, classic depiction of the timeline of structure formation. So now we've gone up to the largest scales, and now I'm going to try and go back down to the smallest scales, but forward in time from the beginning. So we have in the very, very earliest moments of the universe expanded extremely rapidly, meaning basically what was our observable universe was in a very, very, very small section of space, and that expanded almost, I don't want to say faster than the speed of light, but because that's not quite right? But extremely quickly. And that is what helps to explain lots of features in this cosmic microwave background radiation, this idea of very, very quick early expansion, which we call inflation. And then in that very, very early time, there was lots and lots of light. The universe was very dense still, and it was still expanding quite a bit. And as it expanded, it started to cool. In those very early moments, there were just neutrons and protons, the constituents of atoms. And as it started to expand and cool, those neutrons found protons and they started to form some very simple elements. So this is showing a logarithmic time scale. So this just means this is 10 seconds, this is 100 seconds, this is 1,000 seconds, and this is 10,000 seconds, okay? So just like I was going up factors of 2, this is going up factors of 10 for the 1 to the 4 here, okay? This is also logarithmic, but this is basically just showing you how much of different elements there are. So you can see at the top, the black, that's hydrogen, the most abundant element in the universe. And during this early moments, this is 10,000 seconds, so this is maybe a few hours, right? And this is really just, most of the stuff goes on in the first few minutes, is we turn what was almost entirely hydrogen into trace amounts of helium, deuterium, helium-3, and other weird stuff, very, very small amounts of other weird stuff. So this is how we get the very first elements in the universe, mostly helium, mostly hydrogen, a little bit of helium, and very trace amounts of other things. As you probably know, we are not made of only hydrogen and helium. We're made up of mostly oxygen and carbon and hydrogen. So you might ask yourself, where does that stuff come from if it didn't come from the beginning of the universe? And this is a periodic table of the elements showing you for each element where we think it's principally formed, where it mostly comes from. And as you can see here, that Big Bang fusion, the blue stuff that I was talking about before, that's hydrogen and helium, pretty much all from Big Bang. That's a lot of the stuff that's in your body too. We're 70% water, H2O. All that H is from the beginning of the universe. The other things that we're made of, for the most part, are these things, carbon, nitrogen, and oxygen, and they mostly come from the death of stars. So all of the carbon and nitrogen and oxygen in your body was formed through fusion in the core of a star that lived for billions of years and then died, exploded, and shed those elements into the gas in galaxies that then formed into another star, another solar system. So the coolest fact in astronomy that I have to always communicate in every talk is that you are made of stars. Back to our timeline. So we had that early universe expansion. We've made the first few elements, and then the universe was expanding, cooling, until eventually the light that was bumping around into atoms in that very early part of the universe it got not dense enough. It basically expanded enough that the light could free stream forever. And that's the cosmic microwave background, the stuff I was showing you before. And then not a lot happened for a while. Basically, structure started to form in the universe. And I wanted to show you what that looks like. So hopefully this movie is worth my showing it here. So this is going to be a movie of a simulation of structure formation in the universe, going from the first few 100 million years of the universe, so when the first galaxies started to form, all the way down to the universe as it exists today. So you can see at these early times, there's structure for sure, but it's kind of relatively uniform. And as we go forward, you'll see that these structures begin to get denser. Things start to collapse into these, what we call cosmic filaments. And those filaments seem to feed matter onto these hubs in the filaments where the most massive clusters of galaxies are formed. As we go forward in time, the scale of the largest scale structures in the universe gets bigger and bigger. And the galaxies that were forming in these filaments, you see little bits here and here, kind of continually feed into these larger clusters of galaxies. This particular movie is sort of centered on one of the largest clusters of galaxies that formed in this simulation. going all the way down to redshift 0. So the little the z equals in the top right here is giving us an idea of time, which I don't have time to explain, but this z equals 0 is now. It's the important part. So everybody responsible for making this movie, you'll notice that my name is not on there because I did not help. I took this from the internet. So that's how we start to form the first structures in the very, very early universe. Like I said, in those first galaxies, the first stars that formed in the first galaxies were made entirely of hydrogen and very little amounts of helium. With JWST, we are starting to see far enough back in the history of the universe that we're seeing those first galaxies forming. This is an image from the JWST telescope, and zooming in onto a tiny little pixel here, this little blur is the highest redshift, or basically furthest away galaxy that has ever been detected. And it had formed only about 280 million years after the Big Bang. You notice that this diagram, which comes from before JWST was launched, had listed that, oh, the first stars form about 400 million years after the Big Bang. And with JWST, we're starting to see that that is not quite correct. We're seeing the formation of massive galaxies much earlier than basically the earliest models had predicted. I am somewhat involved in that research, but I won't have too much time to talk about it. Okay, so we go forward again. Remember in that movie, we were getting down to today, basically, but really on really large scales. We were looking at the formation of structure of huge clusters of galaxies. And now I'm going to show you another simulation, but now focused on one galaxy that looks a lot like the Milky Way. And within this galaxy, we see a disk of stars, but also a disk of gas. That's another galaxy falling into this one. We're going to fly through the disk of gas, which is all that dark red stuff. And we're zooming through this disk as it's rotating around, zooming out, and seeing those clouds of gas, the dark stuff, is what collapses under gravity and forms the new young stars, which are the preferentially blue things that you see here. Let's see if that... Okay, so we've gotten down to, from the formation of structure, down to the formation of galaxies, and finally, within the galaxy, those clouds of gas, how do they form stars? This is one of the nearest by star-forming regions, the Orion Nebula, which, if you've seen Orion's belt in the night sky, which is very visible here during the winter, you would note, so Orion's belt is these three stars. If you imagine Orion's belt as sort of the top left edge of a square kite, then the string of the kite, which is this little, it's called Orion's dagger, that's the Orion Nebula, which is a nearby massive star-forming region. Within this is a big cloud of gas. The total weight of that cloud of gas is maybe 100,000 times the mass of our sun. And it will make maybe 1,000 times the mass of our sun in stars. And in particular, it's made a few very massive stars that are right in the center here. It's called the trapezium cluster. And those very, very massive stars, they're bright. They're extremely bright. They have very, very hot atmospheres, and they basically have enough energy to destroy the cloud in which the stars are forming. And that's the process that you're seeing here. These things have very hot winds that basically run into this gas and blow the whole cloud apart. And that's why, even though the whole cloud weighs 100,000 times the mass of our sun, only 1% of that or so is going to turn into stars, because the process of star formation sort of halts itself. And that is the main focus of everything that I spend my time working on, but that's all I'm going to talk about. So within these big clouds, you form individual star systems, just the same way that on galactic scales, gas cools, and the gas is spinning a little bit. So when it cools, it loses energy, but it needs to keep spinning because it's not losing that angular momentum. And that's why when you collapse and collapse, but you need to keep spinning, you form a disk. The same thing happens around a forming planet. You form disks, which is where we basically see it happening. So it's fair enough to say that we know that This is how we form planetary systems in disks. Basically, there was a protoplanetary disk around our solar system in its very earliest stages. And out of that disk, little granules of protoplanets formed and collapsed under gravity and formed their own systems, their own planets. And with the ALMA telescope, which is a radio telescope, I believe the whole telescope is at about 11,000 feet above sea level in the Atacama Desert. Giant radio telescope, very, very big project across both the National Science Foundation in the US and in Europe. There's lots of things that this telescope can do, but one of the really cool things in terms of planets that it's been able to help us with is basically directly image the formation of protoplanetary systems, and that's what I'm showing you on the left here, a bunch of observations from this D-SHARP program, which shows protoplanetary disks. So in the center here are stars, very, very early star formation. And the disks that we're seeing around here is that disk in which all of these planets will form. In particular, you see a bunch of gaps in these disks, which is where we assume that there are new planets forming. They're basically carving out the gaps in the disk. Just to give you an idea of scale on these images, the Earth's orbit would be within 1 pixel, basically. So these are quite large scale images of nearby star-forming regions, or protoplanetary disks. Okay, so that gives us an idea of how we got here, how we got to having a system of planets around a star like the sun. With that, I will leave it there. Thank you.
We are happy that you chose to watch a Humanism Today video. If you want to learn more about humanists and free thinkers of Fairfield County, or HFFC, or become a member, please go to hffcct.org. If you like this video, you might like one of our videos above, or one of the other videos or podcasts at hffcct.org. Be sure to subscribe to our YouTube channel by clicking the subscribe button above. Until next time, keep questioning, keep learning, and keep thinking humanistically.